Version of the course, MMI701, Multimedia Signal Processing. This week and the following week, we're going to talk about frequency domain analysis of signals. You may remember from last week's lecture the direct set transform. We obtained the direct set transform by multiplying each sample of our signal by z to the power minus n and adding everything up, where we assume that z is a complex number, which in here is represented in polar form as re to the power j theta. Another transform which is similar and which forms the basis of almost all signal processing is the Fourier transform. The origins of the Fourier transform is based on the analysis of periodic signals and was proposed by Joseph Fourier in 1822 for the analysis of real-valued periodic signals. That is why we're going to start with continuous time periodic signals. So let's assume that we have a signal x of t, which is a function of the continuous time variable t. If the signal is periodic, then x of t0 for any t0 is going to be equal to x of t0 plus t sub p, where t sub p is the fundamental period, which is equal to 1 over f0, where f0 is the fundamental frequency. So this is fundamental frequency. The idea behind Fourier transforms is to express a periodic signal in terms of complex exponentials. Now, in its original formulation, Fourier used sinusoids only because he was dealing with real-valued signals. But in our case, we're going to use the complex exponential because it makes things much easier and more tractable. So here is the Fourier series expansion, continuous time Fourier series expansion for our periodic signal x of t. We're expressing x of t in terms of a linear combination of complex exponentials, e to the power j2 pi k f0 t, and we're using ck, the Fourier series coefficients, in this expansion. Now, this is called the Fourier series. And also called the synthesis equation because you're synthesizing x of t. Okay, and one other thing that we should remember is that k is an integer. So it can be any integer. It can be negative or positive. So k is an integer, as is implicitly seen in the summation bounds. Okay, so then the question is, yes, it is nice that we can express our signal by using this expression, but how do we obtain the Fourier series coefficients? So we obtain the Fourier series coefficients by projecting our signal onto the basis formed by complex exponentials again and integrating x of t times e to the power minus j2 pi k f0 t within one period of the signal. So we're using an arbitrary t0 and the fundamental period of our signal, and we're averaging the integral in the given duration 1 over tp. So this is how we obtain the Fourier series coefficients. So Fourier series coefficients. All right, So let's try to find out the Fourier series coefficients of x of t equals to cosine 2 pi f0 t. In here we can identify our signal, the fundamental frequency of our signal, as f0. So f0 again is the fundamental frequency. So we're going to use that fundamental frequency in our expansion. This is how we would do that. So we can just write the integral which we use to calculate the Fourier series coefficients, 1 over Tp from an arbitrary t0 to t0 plus Tp. It shouldn't matter which t0 you choose, really. And cosine 2 pi f0t, so this is our signal, times e to the power minus j 2 pi f0 kt, and we're going to integrate over t. Now here's a little trick that we're going to use. We're just going to write a little note here, and that is expressing our signal, our cosinusoidal signal, in terms of complex exponentials. Cosine 2 pi f0t is equal to 1 over 2 e to the power j 2 pi f0t plus e to the power minus j 2 pi f0t, right? So this is something that we already knew. And when we substitute this into our integral, we're going to have, just write it a little bit here so that it's aligned, sort of. Okay, 1 over 2 Tp. We're going to have two terms from t0 to t0 plus Tp, e to the power minus j 2 pi k minus 1 f0t dt plus from t0 to t0 plus Tp, e to the power minus j 2 pi k plus 1 f0t dt. Now the question here is this: what is the integral of e to the power minus j 2 pi k f0t? So let me just pose it as a little question here. So what is 1 over dp t0 plus Tp e to the power minus j 2 pi k f0t dt? So we'd like to find this one out, and we can show that this is equal to 1 over Tp e to the power minus j 2 pi f0 kt over minus j 2 pi k f0. We're integrating with respect to the time variable, and we will calculate this from t0 plus Tp to t0, which is going to give us minus 1 over j 2 pi k e to the power minus j 2 pi k minus 1 e to the power minus j 2 pi k f0 t0. So this is what it's going to give us. Now we know that this is going to be 1 unless k is equal to 0. So let me just remind you, by the way, that this is going to only hold when k is not equal to 0. When k is equal to 0, whatever we have inside this integral is 1, so we're going to have 1 as a result, right? Otherwise, we're going to have this expression, but we know that for every integer k, except k equals to 0, because we dealt with this as a separate case, as a special case, this is going to be equal to 1, which means this whole thing is going to be equal to 0, which means this is going to be equal to 0, unless k is equal to 0. When k is equal to 0, it is equal to 1. So let me just write it down here. When k is equal to 0, this integral 1 over tp e to the minus j 2 pi f0 t dt t0 to t0 plus dp is equal to 1. Which tells us that only when k minus 1 is 0 and k plus 1 is 0, we're going to have non-vanishing integrals in here. So when k is equal to 1, for instance, we're going to have this first term equal to 1. So this term equal to, tp. Otherwise, the second term is going to be tp, which means we can calculate the Fourier series coefficients as c1 equals to 1 over 2, c minus 1 is equal to 1 over 2, and all ck equals to 0 for k is not equal to plus minus 1. Okay, so that is nice. As a matter of fact, we didn't even have to take the integral to find this out, because in this expression, we already had it. The two terms that make up cosine 2 pi f0t already give us the coefficients of the Fourier transform 1 over 2. Okay, so far so good. So if our periodic signal is real valued, so that is x of t is in R, then we have the following symmetry relations. Ck is equal to the conjugate of c minus k, which is equal to the absolute value or radius of ck, modulus of ck, and the times a complex exponential e to the power j theta k. So this is just some complex number. So why is that again? So let's try to write it down, why that is the case. So let's write ck. I'm going to skip the bounds. This basically x of t e to the power j 2 pi f0 kt there's got to be a minus sign in here, dt, and let's write c minus k as 1 over tp x of t e to the power j 2 pi, because minus comes from minus k, f0 kt dt. Now you can see that since xt is real value, the conjugate of c minus k is equal to ck, which is something which holds for real signals only. And because of that reason, we can write x of t as, well, it's an open form, so to speak. So we can write our Fourier series as a combination of the zeroth Fourier series coefficient plus k from 1 to infinity 2 times the modulus of ck times cosine 2 pi k f0 t plus theta k, where theta k again is the phase of the Fourier series coefficient k. A relation which has a name which we all know as Parseval's relation, but it also has another more specific name as Plancherel's formula, can be derived for continuous time periodic signals. So this is the Parseval's relation as we know it. We're just saying that the average power of our periodic signal is equal to the sum of squares of Fourier series coefficients, all Fourier series coefficients. So how do we derive that? It is pretty simple actually. We just write Px, which is the average power, that is 1 over Tp, in some interval Tp, x of t squared dt. Now, assuming that our signal is complex valued, so this is true for the general case as well. I mean, it's much easier to show it this way, so that is why we're using the complex conjugate. So we're going to use the definition for the absolute value squared of x of t, so that is x of t times x conjugate of t. Again, if x of t is real, x conjugate of t is going to be real as well, so we're not losing anything here. dt. Okay, so let's write it down. 1 over dp, integrating in tp. And let's write x of t as x of t, and let's write the conjugate of x of t as ck conjugate e to the power minus j2 pi f0 kt dt. Okay, so this is x of t conjugate. That is why we have a minus sign in here, and that is why we have a conjugate sign in here. And we integrate over dt again, over t again. And let's swap the summation and the integration. So we're just going to use summation outside integration. So let's write ck conjugate, and we're going to integrate over tp. I think we forgot to add 1 over tp here, so let me just edit. This is 1 over tp. And what else? We have x of t e to the power minus j2 pi f0 kt dt. But what else do we know? This is so 1 over tp times this integral is equal to ck, which will eventually give us, for all k, absolute value of ck squared. So this is Parseval's relation. Again, this is a different name, Plancher's formula, but that's just detail. So this is the Parseval's relation. Now, what you see here is the power spectral density. That is CK squared plotted for each K. We know that CK is equal to absolute value of CK times e to the power j theta k, and absolute value CK squared is the power spectral density. For all K, basically. And theta K is the phase. That is the angle of CK. Now you may remember from last week that we can represent any complex number in terms of its radius and phase pretty easily. So this circle has a radius of, say, CK, and the number that we're trying to represent is on this circle with an angle theta k. So this is our way of representing this number, this complex number. So this is the real axis and this is the imaginary axis. Okay, so one thing that you may see is that power spectral density is obviously positive value, so that it cannot be negative. And the other thing is, for a real signal, it is symmetric with respect to k equals to 0. Okay, so continuous time periodic signals are, kind of interesting. It was a starting point for Fourier anyway. But more interesting signals in real life are continuous time aperiodic signals. Now, you rarely ever, at least in the multimedia domain, you rarely ever work with periodic signals, well, continuous time periodic signals. So the blue signal that you see here is a periodic signal, right? So let us define a signal which is exactly fitting to the periodic signal in one period, but 0 elsewhere. So we know that the periodic signal, we can calculate, for the periodic signal, we can calculate the Fourier series coefficients as, so let me just write here to save a little bit of space, Ck equals to, that is kind of annoying to write it over and over, but so minus Tp over 2, say, and Tp over 2, so one period, and x periodic of t, x sub p of t, e to the power minus j 2 pi f0 t, well, kt dt. Right, so this is our Fourier series coefficients. Now, let's assume that we have a signal. So this blue signal is xp of t, say. Okay? And let's assume that we have a signal x of t. That's this yellow signal, x of t, which is equal to xp of t in one period from minus Tp over 2. So let's call this. So let me just draw this. And this as well. So So let's say this is minus Tp over 2, and let's call this Tp over 2. From minus Tp over 2 to Tp over 2, our new signal x of t is equal to the periodic signal xp of t. And it's 0 elsewhere, as you can see, right? So this is our signal. Then we can write, for this kind of a signal, Ck, the Fourier series coefficients that we had for the periodic signal, using this new signal. And it's going to be equal because we don't really care about the values of our signal outside minus Tp over 2 and Tp over 2. So we can just express this as from minus infinity to infinity instead of minus Tp over 2 to Tp over 2, minus infinity to infinity, x of t e to the power minus j 2 pi f0 kt dt, right? Now, how could we do that? We know that, again, outside plus minus Tp over 2, our new signal is 0, which means adding whatever part we have outside these two values does not change the value of the Fourier series coefficients, regardless of whether or not this expression makes sense right now. So let us now define the continuous time Fourier transform. So I'm just going to use a different color for that. I'm just going to use blue, x of f. This just by definition, from minus infinity to infinity, x of t e to the power minus j 2 pi f t dt. Now we're going to come back to this, but let me just write that this is the continuous time Fourier transform. Or, since we're analyzing our signal, not synthesizing but analyzing, we're going to call this analysis equation. Okay, so this is our analysis equation. Now, remembering what we had for Ck, and Ck is here, right? So this expression. Can we express x of f, our analysis equation, in terms of, can we express our Fourier series coefficients in terms of the continuous Fourier transform that we have just defined? So if you want to write Ck in terms of the newly defined continuous time Fourier transform analysis equation, that will be 1 over Tp x of kf0. So at one specific frequency, kf0, these two signals are going to be equal. So these two coefficients are going to be equal. Then what else? So we can express f0 as 1 over Tp, which means we can express Tp times Ck equals to x k over Tp. We expressed f0 in terms of the fundamental period. And let's also express our periodic signal, xp of t. Just remove this arrow, it doesn't make any sense here. So let's express xp of t as a Fourier series for all k, Ck e to the power j2 pi f0 kt. Okay, that's nice. Then let's express ck in terms of our newly defined Fourier transform, which means we're going to have 1 over Tp x of k over Tp, so this is ck, times e to the power j2 pi f 0 kt. Okay, so we're going to have a little trick in here. Let's define delta f as 1 over Tp. In other words, let's pick Tp so large that we end up with a frequency which is so small, or delta f which is so small, which means we can express xp of t. Let me just put an arrow here, so we can express then xp of t as, for all k, x of k delta f, because 1 over Tp was delta f, e to the power j2 pi f, sorry, delta fk, delta f kt times delta f. Alright, so where are we now? We have just said that we obtained the continuous Fourier transform from the Fourier series with a clever trick. So we haven't done anything else. We're just linking the analysis equation with the periodic signal, with the Fourier transform of the periodic signal for delta f being very small. We have picked the period to be very large in that sense. So when we do that, what we essentially get is, at least when delta f is very small, what we essentially get is an integral. So let me just explain to you how this happens. So let's just write a little note here to see the link. Some of you might have seen the link already, but let me just write it. So we have just expressed, we have f of x dx. We're expressing this as a limit delta x, as delta x approaches 0, sum of f k delta x times delta x. So as x is very small, we're just getting the numerical quadrature, so to speak, of our function in here. That will mean that our periodic signal then so if we let delta f approach 0, then xp of t is equal to x of t. In other words, we can obtain the synthesis equation as x of t equals to, from minus infinity to infinity, x of f e to the power j 2 pi f t dt. Okay, and this is our synthesis equation. or inverse continuous time Fourier transform. Inverse continuous time Fourier transform. So again, our analysis equation is x of f equals to from minus infinity to infinity x of t e to the power minus j 2 pi f t. And our synthesis equation is x of t is equal to minus infinity to infinity x of f e to the power j 2 pi f t df. Okay, so these are the analysis and synthesis equations, or continuous time Fourier transform and continuous time inverse Fourier transform. So one little thing, I mean, it is possible to express omega as a radial frequency, 2 pi f as a radial frequency, which is going to mean that we just change our expressions a little. So we can express the same Fourier transform in terms of the radial frequency as x of omega from minus infinity to infinity x of t e to the power minus j omega t. And synthesis equation is similarly different because d omega is 2 pi df. We have a matching equation which is 1 over 2 pi times from minus infinity to infinity x of omega e to the power j omega t df. So this is just expressing the whole thing a little bit more differently. So this is not, I'm sorry, this is not f, but this is omega. Okay, let me just write it more clearly. So this is d omega. Sorry about this. Okay, so let's have a look at this example. X of t is equal to 1 over t between minus t over 2 and t over 2 and 0 elsewhere. So this is 1 over t. Okay, so what is the Fourier transform of x of t then? So we can write it very easily, and let's do that. X of f is equal to from minus infinity to infinity x of t e to the power minus j 2 pi f t dt, which is equal to 1 over t from minus t over 2 to t over 2 e to the power minus j 2 pi f t dt. And this is equal to minus 1 over j 2 pi f t e to the power minus j 2 pi f t, but t is from minus t over 2 to t over 2. And when you calculate this, you're going to end up with sine pi ft over pi ft. Now there's a question. So this is the sinc function, as some of you might already know. So let me just write this down with red so that we know that it's a node. Sinc function, sinc of x is equal to sine x over x. So this is the sinc function. Now here's a little question for you. What is the value of sinc function at x equals to 1? So, sorry, x equals to 0, I'm sorry. So what is sinc 0? Now we know that sinc has some value outside, right? This is a linearly decaying sine function. So the sinc 0 is limit as x approaches 0 sine x over x, which is, by using the small angle approximation, we have x over x, and that is equal to 1, which means sinc 0 is 1. So if you wanted to draw the sinc function, it would look like a sinusoidal signal which is weighted by 1 over x. So, yep. Okay, so this is our axis, and so let's call this x, and let's call this sinc x. Our sinc function is going to be something like this. And at 0 it's 1, and at pi and minus pi it's 0, etc., etc. Okay, so let's talk a little bit about how Parseval's relation is expressed in continuous time Fourier domain. So I would have to make a little correction in here, because it's not x, it's not lowercase x, but it's capital X. So this is capital X, F. Okay, so let's just try to do the same operation on this. So first of all, let's see what this means. We say that the energy of our signal x of t, which has a finite time support, is equal to the integration of its Fourier transform squared over all f. So that's the Parseval's relation for discrete time aperiodic signals. I'm sorry, continuous time aperiodic signals. Was there a problem in the others? No. Okay. So continuous time aperiodic signals. So let's have a look at how we do this. So let's first write energy E of x is equal to x of t squared dt, which, as you may remember from a couple of slides ago, is x of t times x conjugate of t. It's going to be a neat trick for Parseval's relation, deriving the Parseval's relation. And that is equal to, from minus infinity to infinity, x of t. Now we're going to write x conjugate of t in terms of the Fourier transform of x of t. So we're going to conjugate everything basically. So x conjugate of f e to the power minus j2 pi ft df, and we have another one dt outside. Okay, so we're going to change the order of integration. So we're going to put x conjugate of f in here, and x of t e to the power minus j2 pi f t df sorry, the order has to be different. So this is dt from minus infinity to infinity again, and df on the outside. But we know that this is x of f, which is going to give us from minus infinity to infinity x of f absolute squared df. So that is the Parseval's relation for continuous time aperiodic signals. Now, let's define the energy density spectrum. Now we have defined x of f as the magnitude of x of f times e to the power j theta f, where theta f is the phase spectrum and the absolute value of x of f is the magnitude spectrum. Now, based on this, we define the energy density spectrum as the square of the absolute value of x of f. That is called the energy density spectrum. Now, there is one interesting thing, or one important thing rather. Sometimes people get confused and say power for signals which have finite time support and energy for signals that are periodic. Don't get confused. If a signal has a finite time support, you're going to be talking about energy. If it doesn't have a finite time support, if it extends from minus infinity to infinity with some non-zero values, then you're going to call power. Then you're going to define the power of a signal. So we have covered this during the second week. So power signals, energy signals, just to make sure that you understand the difference in the terminology. And the energy density spectrum is always positive because it's the square of an absolute value of something. And if you have a real valued signal, then it's symmetric with respect to frequency. So we calculated the continuous Fourier transform of the rectangular pulse as sinc pi ft. And this is, the blue curve is sinc pi ft. And the yellow curve is the square of it. That is sinc pi ft squared. That is the energy density spectrum of sinc. Now, how about discrete time periodic signals? Now, we discussed discrete time signals, right? So, obviously, we should have some way of extending our continuous time methods to discrete time methods. By the way, something I forgot in the previous slide, sorry, three slides ago. Now, we mentioned the switching of the integrals, two integrals. Now, this is only possible under some conditions. I'm not going to go into this, but please do search for Fubini's theorem. It's going to tell you the necessary conditions for Fubini's for the switching of integrals work. Fubini theorem. So you're not allowed to change the order of integrals for every case. It needs to have certain conditions satisfied. Okay, so let's continue with this. Discrete time periodic signals. So a periodic continuous time signal was defined as f of t. So continuous time periodic signal f of t is equal to f of t plus capital T, that's capital T being the period, right? So more generally, f of t is equal to f of t plus kt for k an integer, any integer, really. Now for discrete time signals, discrete time periodic signals, as we saw before, discrete time periodic signals, we have x of n equals to x of n plus kn, where n, capital N, is the fundamental period. So this is a discrete time periodic signal. So the first equation that you see here is a discrete time Fourier series, or synthesis equation. Why synthesis? Because we're synthesizing the signal from its Fourier series coefficients. So let's try to get the synthesis equation. Okay, I'm just going to write it down here. Sorry, analysis equation. So let's have a look at what we have. In here we are expressing again our periodic signal in terms of complex exponentials, as a linear combination of complex exponentials, but these complex exponentials depend on the sample index and as well as the Fourier coefficient index k. And we're using a fundamental frequency of 2 pi over n, fundamental radial frequency of 2 pi over n, because n is our period now. So let's have a look at how we obtain the analysis equation. So we're going to start at a slightly strange place. That is, we're just going to say that for all terms k from 0 to n minus 1, e to the power j 2 pi over n, kn is equal to n if k equals to 0 and 0 otherwise. Okay? So let's try to express the analysis equation that we may have in our mind in a way similar to what we did with the other continuous time signals that we analyzed up to this point. So let's write n from 0 to n minus 1, x of n, so that is one period of our discrete time periodic signal, x of n, one period of x of n, e to the power minus j 2 pi over n kn. And let's substitute our synthesis equation in place of x of n, so that we have for n from 0 to n minus 1, and for k from 0 to n minus 1, ck e to the power j 2 pi over n k minus l this time, because instead of n let's use k minus n, not l. Otherwise I would have to change many things back there. Oops. K minus l n. Apologies, I probably messed up with this in here. I should have had L in here. Okay, k minus ln. And then we're going to continue with this. We're just going to put the inner sum out and the outer sum in, so n from 0 to n minus 1 e to the power j2 pi over n k minus ln. Now we know that this sum is going to be equal to n if and only if, so this inner sum is going to be equal to n if and only if k is equal to l. That is going to make the exponent of e 0, which means we're going to have n such terms, so we have n and ck. So we're going to end up with this expression being equal to n ck. Or in other words, if we divide our first expression by n, we're going to end up with the analysis equation. Then ck is 1 over n for n from 0 to n minus 1, x of n okay, so let me just move things. I just want to move things a little, but I wonder if this is going to be a good idea. E to the power minus j 2 pi over n kn. Okay, which is the expression which you see here already. The analysis equation. Okay, so what else can we do with this? Let's define some omega k as, so let's put a little note here. Let's define some omega k as 2 pi k over n. So that's our omega k, which we have here already. Okay. Then let's define sk of n, if you like, as e to the power j2 pi over n kn equals to e to the power j omega kn. So this is how you would make the link between your discrete time or discrete frequencies 2 pi over n and the radial frequency omega k. But we know that this is also periodic. With 2 pi, which is going to mean eventually that ck plus n is ck. That means the Fourier series coefficients are also periodic with n. So let me just write it here. The Fourier series coefficients are also periodic with capital N, that is the fundamental period. Okay, so average power of discrete time periodic signal. We will first, again, as we did with continuous time signals and discrete time signals, as we're going to do for discrete time signals next week, discrete time aperiodic signals, let's calculate the energy or power of our signal. So let's write what we have. You're going to find this a little bit of a boring exercise because we're doing the same thing over and over for all derivations of Parseval's relation or Plancharel's formula. But we have this. So let's write the power of our discrete time periodic signal. So we're going to get the sum in one period only. That is from n from 0 to n minus 1. X of n squared. This is equal to 1 over n from 0 to n minus 1. We're going to write it as x of n times x of n conjugate. And then we're going to express this as 1 over n from 0 to n minus 1. X of n, and we're going to write the complex conjugate of x of n in terms of its Fourier coefficients, k from 0 to n minus 1, ck conjugate, e to the power minus j2 pi over nkn. And this is equal to 1 over n. Let's put ck conjugate out and change the order of summation as well. For all n from 0 to n minus 1, x of n e to the power minus j2 pi over n k. And but we know that this is so this combination of this and this is ck. We have for all k from 0 to n minus 1, which is equal to the power. So that shows that Parseval's relation also holds for discrete time periodic signals. Okay, so properties of discrete time Fourier series. If you have a real valued signals, it's easy to show that the Fourier series coefficients are complex conjugates of each other for positive and negative k, which also means that their radii are the same, or magnitude are the same, and their phases are reciprocals of each other, so not reciprocal, so phase of ck is minus phase of minus c minus k, and since we have periodicity, we have ck equals to c n minus k conjugate. And if you wanted to write this relation, we have C0 equals to Cn, C1 equals to Cn minus 1, etc., etc. Cn over 2 equals to C conjugate n over 2. Now that's interesting. What do we mean by this? So something being the, well, conjugate of something being equal to the same thing, which means when n is even, Cn over 2 is real. Okay, some little fact about Fourier series coefficients. All right, so let's have a look at an example. So the question is this: what are the Fourier series coefficients of this pulse train? So this is not an impulse train, but a pulse train. And a pulse train has a series of pulses, then a series of zeros, a series of pulses, and then a series of zeros. So let's have a look at it in more detail. Say in this case we have 10 impulses and 10 zeros, 10 impulses and 10 zeros, etc., etc. And you can see that this is periodic. This is a periodic discrete time signal. So first of all, this signal has a period 20. So let's write it down. So period is 20. Every 20 samples it repeats itself, because we have 10 ones and 10 zeros. We have a period of n equals to 20. Okay, so it is discrete time periodic. We have just established that. And let's calculate the Fourier series coefficients of the signal. Ck is equal to 1 over n, and from 0 to n minus 1, e to the power minus j 2 pi over n, kn times, x of n. But we know that x of n is 1 or 0, so we're going to work that out. So this is equal to 1 over n, and from 0 to n minus 1, e to the power minus j 2 pi over n kn. But we know that this is a finite series, which we can easily convert to the value it will converge to, and that is 1 over n, 1 minus e to the power j2 pi k, sorry, j pi k, because we are integrating up to n over 2 minus 1. No, sorry, this should have been, I'm just going to have to write it down once again, I guess. So let me just clear this and write it once again. Yep, it's got to be, So this is equal to 1 over n, and from 0 to n over 2 minus 1. Sorry, that's the upper limit has to be n over 2 minus 1, because we only have ones for the first n over 2 minus 1 samples. Sorry, n over 2 samples. And this is e to the power minus j 2 pi over n kn. And this is going to converge to 1 over n, 1 minus e to the power minus j pi k over 1 minus e to the power minus j 2 pi over n k. Okay, so for instance, for several values, say for instance for k equals to 0, what do we have? For k equals to 0, we're going to have C0 equals to 1 over 2, because when we substitute k equals to 0 here, this is going to be 1, and we have n over 2 samples in the summation. So in this summation we're going to have n over 2 samples, and we divide by n, which means C0 is 1 over 2, and we can calculate all the rest that way. Okay, so this concludes the video for this week. We will continue with discrete time aperiodic signals in the following week's videos. Please do check the IPython notebook. If you haven't installed Python and Jupyter on your own computer, please do so. If you cannot install these for some reason, you can use Binder, which I provide links to on Auth2 class. You can use that one as well. It's interactive, so you can play with the numbers there and you can see how it works. It is quite handy in that way. You're going to see some examples which are linked to this week's videos. So please do check those examples. Thank you very much for listening and see you next week.